Now we are going to study steady 1D conduction through a plane wall with internal generation. We saw steady 1D conduction through a plane wall without generation. The results were heat transfer, the temperature distribution was linear. See, without internal generation, two results we derived. The temperature distribution was linear and the heat transfer rate was a constant. This is very important to note. Now with generation, what is the difference that we will see? Temperature distribution is going to be quadratic or it is a parabola, it's not a straight line. And the heat transfer rate will depend on x, is not a constant. Instead, the heat transfer rate itself will be a function of x. Depending on the value of x, the heat transfer will change. So these are the two results that we are going to derive, but it will differ. When there is no generation, temperature is linear. When there is generation, temperature is quadratic. Heat transfer was a constant if there is no generation. Heat transfer will be a function of x if there is generation. Have this in mind, and now we will start the derivation. Now this setup, you again have a plane wall. The left temperature is TW1 and the right temperature is TW2. Now there is a non-zero generation. This wall is a part of a nuclear reactor or something is happening in the wall which is generating heat on its own. Not heat entering the wall but generating its own. Now x, I am going to change the origin. I am going to take x as the center. The center of the wall, I am going to take the origin for x. So this will be x equal to L and that will be x equal to minus L. So that the width of the wall I am going to take it as 2L. From minus L to L. Is this clear? So we'll start, and if you want to locate this in the data book, page number 47 in HMP data book, slab with asymmetric boundary condition. It's the last in the page number 47. Okay, let's start with the differential equation governing this. Differential equation is rho square t by rho x square plus rho square t by rho y square plus rho square t by rho z square plus q dot by k equal to 1 by alpha rho t by. Because it's a plane wall, we are going to use Cartesian coordinates. So Cartesian coordinates, that's the differential equation. Now assumptions. What is the first assumption? Steady state. So this term is going to be 0. Now with generation, so you cannot throw this term, you have to have the term 1D. I'm going to assume temperature is only a function of x. As I move in x, the temperature changes. If I go in y or if I go in z, the temperature is not going to change. So derivative with respect to y, derivative with respect to z, they are always given. Now my governing differential equation becomes rho square t by rho x square plus q dot by k equal to 0. Now because temperature is only depending on x, no other variable is present, I can replace this partial derivatives with ordinary. Is it clear? So this is the first step. We are going to reduce the governing equation to a simpler equation based on the assumptions that we have made. Now what do? You have to integrate this equation. So integrate both sides with respect to x. There is a derivative with respect to x. If I integrate, the derivative is going to go off. So if I integrate this with respect to x, I get dt by dx. This is a constant. If I integrate that, minus q dot by k into x, then you have to add the constant of integration. Now we will integrate once more. Integrate both sides with respect to x. Let us integrate once again. dt by dx will become t. Minus q dot by k is a constant. Integral of x is x square by 2. Plus integral of c1 is c1 into x. Now for this integration you have another arbitrary constant c2. This is clear. So you see temperature is going like x square plus x plus c. Temperature distribution is clearly quadratic. It's a parabola, it's no longer a straight line. How do we find c1 and c2? Boundary conditions. From the boundary conditions. We can find c1 and c2 using the boundary conditions. What are the boundary conditions?
T is equal to T W1 and
See, when x is equal to minus L, t is equal to dw1. We always have t as a function of x. So t at x equal to minus L is equal to dw1. T at x equal to plus L is equal to dw2. These are the two boundary conditions. Now if you substitute the boundary conditions in this equation, you get two equations. One for C1 and C2, simultaneously solve it, you will get C1 and C2. I am not going to do that for you, but I will straight away write the temperature distribution. What is that? From this equation, when you find C1 and C2 using the boundary condition and substitute, you will get something called the temperature distribution. And write it straight away. You can take it as an exercise. You can substitute C1 and C2, find the temperature distribution. T looks like 2 dot by 2k L square minus 6 square plus x by 2L into PW2 minus PW1 plus half PW1 plus PW2. Okay. So this will be the temperature distribution that you will get. Now you clearly see that the temperature distribution is going to be quadratic. How does the temperature look like if you plot, say this is TW1 and that is TW2. If this is high temperature and that is low temperature and heat is being generated in the wall, then the temperature distribution will look like this. It's a parabola. Okay? The temperature will rise, reach a maximum, and then it will fall. Because it's a parabola, it's not going to come like this. And it's not going to reach a minimum because heat is being generated. Heat is being generated, we are also retaining this at high temperature and that at low temperature. So the temperature will rise and then it will fall. So there is a plane at which temperature is the maximum. You see, this temperature is TW1, that temperature is TW2. At this point, the temperature is a maximum. So this plane, or this value of x, this is called x maximum. Not the x value is maximum. At this value of x, the temperature is a maximum. So that is the plane of maximum temperature. Now can you guess what is the direction of heat transfer? How is heat going to be transferred? What direction in which heat is going to be transferred? In a plane wall without generation. We have T1 and T2, temperature distribution is like this. And how was the heat transfer? Heat transfer comes from left to right because this is high temperature and that is low temperature. Here how is going to be the heat transfer?
Here also the heat transfer is going to be from left to right, but there is going to be a slight rise in the temperature.
No. You see that here the temperature rises. This is high temperature and that is low temperature. So heat always transfers from high temperature to low temperature naturally. So in this side of the wall, heat will be transferred like that. McCloskey statement.
Okay.
Heat always flows from hot body to a cold body, or heat naturally flows from high temperature to low temperature. So you see that this plane is very important because on the left side of the plane, heat is going to be transferred in the negative x direction. On the right side of the plane, the heat is going to get transferred in the right, the positive x direction. So the heat transfer will be on both the sides of this particular plane. And the heat transfer on this plane itself is going to be zero. Right? Because this plane is dissipating heat on both sides, there is no heat crossing this particular plane. And for that reason, this plane is called an adiabatic plane. You know, adiabatic means no heat transfer. So this plane on which there is maximum temperature is called an adiabatic plane. We will discuss all these when I derive the heat transfer. But beforehand, from the temperature distribution, you can tell a lot of things about heat transfer. One thing, I repeat again, the temperature distribution is quadratic. It has to reach a maximum somewhere in between. Where the temperature is the maximum, that's a very important plane. I'll call that x location as x max. And the temperature, the maximum temperature, I'll call it as T max. Now if you look at what is the direction of heat transfer, if you are simple-minded, you will say heat transfers from left to right because this wall temperature is high, that wall temperature is low. But it's not true because there is a maximum temperature within the wall. So here you see temperature, this is high temperature, that is low temperature, heat will get transferred this way. On the other side, this is high temperature, this is low temperature, heat will get transferred this way. So heat is getting dissipated on both the sides of the wall from the maximum temperature. So because heat is getting transferred on both sides, there is no heat crossing this plane, and on this plane heat transfer will be 0. Hence the name adiabatic. Is that right? Now we will derive everything and see. Once you have the temperature distribution, how do you derive the heat transfer?
Using
Fourier's law. For Fourier's law, you need dt by dx. So I will differentiate this first. I'm foreseeing that I need dt by dx, so I take a derivative of this. dt by dx is, see, you have L square minus x square. If you differentiate L, it's going to be 0. Differentiate x square, it's going to be 2x. So you have q dot by 2k minus dx. That's the derivative of the first term. Plus x derivative is 1. All the others are constant. 1 by 2L dw2 minus dw2. So this will be dt by dx. I will rearrange this a little bit. Okay, let's keep it that way. Now I will write Fourier's law and derive the expression for heat transfer. The heat transfer rate, Fourier's law, Qx equal to minus Ka dt by dx. A is, now in the plane wall area is a constant, K is already constant. dt by dx I have the expression. So I can write what is Q. Q is minus Ka into minus 2, the 2 gets cancelled, minus Q dot by K into X plus Tw2 minus Tw1 divided by L. So I can take a minus sign inside. Q will be Ka into Q dot by Kx minus or plus Tw1 minus Tw2 divided by L. And so this minus. Now you multiply Ka inside, you get Q dot, K is cancelled, Ax plus Tw1 minus Tw2 divided by Ka Tw1 minus Tw2 divided by L. Now it's very nice. This is the formula for plane wall without generation. That's the heat transfer if we have no generation. This term is the additional term that comes because of generation. This makes the heat transfer a function of x. Now depending on x, the heat transfer is going to change. Is that clear? So this is one thing. Another thing, if you want to find the maximum temperature, how do you find the maximum temperature? With the maximum temperature, dt by dx is going to be 0. Correct? The condition for maximum temperature is at the maximum temperature, the slope is going to be 0. So if you equate dt by dx to 0, then you will get the value of x. So you will get q dot by kx equal to Tw2 minus Tw1 divided by 2L. So x will be k by q dot. So this will be x max. This is the location of the adiabatic. And if you substitute x max here, you will see q will be 0. Q will be 0. At x max, q is going to be 0. So you can try that and play with this equation. This equation is rich in physics, especially because the heat transfer is on both sides. There is one plane where heat transfer is 0, where the temperature is the maximum. So a lot of mathematics will come. You know calculus very well, then it's an interesting kind of a derivation. But all the results are there in the data book. You need not memorize any of the results. You need to understand the results so that you can do the problems effectively.